In this video, we're going to be talking about continuity. Continuity is a very important concept in calculus. Many of the most important theorems in calculus start with, let f of x be a continuous function. And if it's not a continuous function, then we can't apply the theorem. The theorem might be true still, but there's no guarantee of that. It has to meet the condition in order to be able to apply the theorem. So continuity is very important. Now, continuity can be thought of as being able to draw the graph without lifting your pencil off the page. There are graphs that have breaks in the graph, and we've seen some examples of these when we have a vertical asymptote, a jump, a hole, or a displaced point. However, in between these places where they have this discontinuity, they may be continuous. So they may be continuous over intervals within their domain, or even continuous over their entire domain, but their domain is not all real numbers. We're going to start by taking a look at what it means for a function to be continuous at a single point. After we've discussed what it means to be continuous at a single point, we'll look at what it means to be continuous over both an open interval and a closed interval. Let me share my screen with you and we'll get started. These are the learning objectives we're going to be talking about today. We're going to explain the three conditions for a function to be continuous at a single point. And by a single point, we mean at a single x value. So we're looking at the y values and talking about the behavior of the graph at a point x equal a. Then we're going to describe four kinds of discontinuities, which you can already guess what they are. They're going to be the jump, the displaced point, the hole, and the infinite vertical asymptote. We're going to then define continuity on an interval and state a theorem for limits of composite functions. In other words, functions that have been composed with other functions. We use composition all the time in calculus and other subjects in mathematics. We need to know what it means for continuity with a composite function. Finally, we're going to take a look at the Intermediate Value Theorem. This is another important theorem in mathematics because it leads to the proof of the Mean Value Theorem, which we'll cover later this semester. And the Mean Value Theorem is involved in some of the most important theorems in calculus. Let's now turn our attention to continuity at a point. Now, our hand-waving definition of continuity is draw it without picking up the pencil. But we need to make that mathematically precise. So we've already seen four different types of graphs that have breaks in continuity: the hole, the displaced point, the jump, and the infinite vertical asymptote. What we want to do now is we want to look at these graphs and analyze why it is that we have to pick up the graph at that point. And then we want to sort of put that exception into our definition for continuity. So looking at this graph, we're going to start with the hole. When we look at the graph of a function with a hole in it, the reason we have to lift the pencil at the point where the hole is because the function is not defined there. So in order to fix this issue, we need to require that the function be defined at that point. Now, this is also an issue with the vertical asymptote. The vertical asymptote has more than one issue, but again, the function is not defined at the value of a. So it sounds like we need to require that the function be defined at a. Is that enough? And the answer, of course, is no. Next, we take a look at a jump. We'll look at the jump and we'll notice that, in fact, this particular graph is defined at the point A on the left side. However, notice that it is not continuous. We can't draw this without picking up our pencil. So we have a problem here. And the problem is, it looks like the limit does not exist. We have a limit from the left, which is pointing at this y value, and a limit from the right, which is pointing at this y value. The two-sided limit does not exist because in a jump, we have different one-sided limits. So the problem with the jump, whether or not it's defined at one of the endpoints, is that the two-sided limit does not exist. So we know we need to require that the function to be defined at the point. Would adding that the two-sided limit exists at the point solve our problems and make the graph continuous? The answer is no, we still have one graph left. And that would be the displaced point. When we look at the displaced point, the function value f of a does exist. It's right here. Also, the two-sided limit does exist. It is going to be right here. So this value right here, which is L, is the limit as x approaches a of the function. And this value right here is the value of f of a. F of a exists. The two-sided limit exists. This solves the problems in the previous discontinuous graphs, but it doesn't solve the problem here. The problem is we still have to pick up the pencil to mark the displaced point. If we could just move that point right back down into the hole, it would be continuous. So, what is it that we need in order for the function to be continuous when x equals a? Well, we need the function value to be what the limit is. We need f of a to be equal to L, the two-sided limit as x approaches a. If the limit points to the actual value of the function, then we should be able to draw it without picking up our pencil. Let's go ahead and formalize this by writing down the requirements for continuity at a point. First, the function must be defined there. Second, the two-sided limit must exist there. And third, these have to be equal. The two-sided limit has to equal the function value at a. If it fails any of these three conditions, it is discontinuous at the point x equal a. Let's turn our attention to piecewise defined functions. These are functions that often have discontinuity points inside their domain. Let's look at what causes them to have discontinuities, and we'll also look at some that don't have discontinuities. When we're looking at this function right here, I do want to go over how to graph these because I found over the years that students have a great deal of difficulty with graphing these piecewise defined functions. So let's make sure that we understand what we're doing. We have three rules for this piecewise defined function. We'll call them rules 1, 2, and 3. Each piece has its own subdomain of the domain of the function. This piece can only be used between -infinity and 1, but not at 1, which is why we make it a round parenthesis. However, this is a connection point between the pieces of the graph. So we will substitute 1 into the first equation, but instead of making it a solid dot, we'll make it an empty dot or a hole. So I know that when x equals 1, 2x plus 1 would become 3. So when x is 1, y is 3, except it's not really because it's not in the domain of that piece. So I make it a hole. Now, this says only move to the left. So I want to graph 2x plus 1, but only for x in -infinity up to, but not including 1. I can then use the slope and this hole to draw the rest of the graph. So I'm going to come down to left one, down to, oops, I forgot to go left one, down to left one. And then draw the best straight line you can. That's pretty good for me. All right, or you can also take your straight edge, which I do have on my very messy desk right here. That's the first piece. Notice you did not graph it over here at all. This particular piece does not apply except in this domain. Then I want the function value to be 2 right at x equal 1. That would be a solid dot at the coordinate 1, 2. I already know I've got either a jump or a displaced point in my graph. I have to. These pieces don't connect. What about the next rule? Now, this rule only applies when x is 1. It's the only time I'm going to graph just 2. This says graph for x values greater than 1, but not including 1. But again, that's where the piece connects. So I still have to substitute it into my piece function and get a value, but it will be a whole because this is not included in the domain of the third piece. Substituting 1, I get -1 plus 4, which is again 3, which means I just have another whole up here. And then I can graph the rest of it, but only from 1 to infinity, not including 1. So the slope of this line is -1. So I come down 1, right 1, down 1, right 1, etc. This time maybe I should use my straight edge. Well, that was kind of off. Maybe the straight edge isn't enough. Okay. We'll try that again. More or less. Okay, I give up. You're going to have to use your imagination. Now, this turned out to be a displaced point. The function exists here, and it's defined at 2. But the limit from the left points at 3. The limit from the right points at 3. The two-sided limit is 3, which means that it does not meet the conditions of continuity. Let's write down our conditions for continuity. F of A exists. 2, the limit as x gets close to A of the function f of x equals L, or you can write the word exists. Because I didn't put the one-sided notation, this is the two-sided limit. Both of these conditions are met. What about the third condition? The third condition is that the limit as x approaches A of the function f of x must equal f of A. And this is where this one fails. It fails rule 3. Let's go on and take a look at another example with a piecewise defined function. In example 2, we have yet another piecewise defined function. This one does not consist of all lines. We have a cubic as piece 1. We want to know if it's continuous at both -1 and at 3. In order for that to happen, we have to meet our 3 conditions. So let's go ahead and add our conditions in. I think I copied them. I did. Let's move them over here. All right. First, the function has to exist. We're going to start by examining what happens at x equal -1. At x equal -1, is the function defined? Not with the first piece, because this is less than, not less than or equal to. However, this one does. This says that x can equal -1. So I use rule 2 to find out that f of -1 is equal to -1. All right. So I substituted -1 into rule 2 and I got -1. I know then that the function's defined there. What about the limit as I approach from the left and the right? Do they point to the same place? For a piecewise defined function, you need to take the piece on the left of that value and the piece on the right of that value and find the one-sided limits. So the limit as x approaches -1 from the left side applies to the rule x cubed. I can substitute the value of -1 in, and I get -1 cubed, which equals -1. Then I look at the limit from the right side of -1. That uses the second rule where the x values are greater than or equal to -1. The rule is 2x plus 1. When I substitute -1 into this, I again end up with -1. Because the limit from the left and the right point to the same value, then I know that the two-sided limit exists and is equal to -1. This meets rule 1. This meets rule 2. Rule 3 is the easiest of them to apply if the first two have been met. It says, is the function value equal to the two-sided limit value? And ours is. So we can say in this last one that f of -1 equals -1, which is equal to the limit as x approaches -1 of the function. This function is continuous at -1. Now, the other value we wanted to establish continuity at is at 3. Looking at 3, the first condition to be met is that the function exists at 3. When I look at the two rules, though, on either side of 3, notice that both inequalities are strict. The middle one does not include 3, and the lower one does not include 3. That tells me right there that f of 3 does not exist. If f of 3 does not exist, then it can't be equal to the two-sided limit, even if it does exist. So it automatically fails rule 1 and 3. I could still check to see if the two-sided limit exists, but there's no need. I already know that it's not continuous. If one condition fails, it fails. Math tends to be a little unforgiving. It's all or nothing. Let's go ahead and graph this now and see if our graph meets our conclusions. So I'm going to look at the domain of the first piece, which is all the values from -infinity up to -1, but with a hole at -1. I'm going to graph the hole first. -1 cubed is -1. So I get a hole right there, and I made it great big so it would stand out. And then I need to move to the left, so I'll go ahead and graph -2 cubed, which gives me -8, which is going to be down here. Remember, this is part of a cubic, but only this part right here. It does not include the other part of the cubic. Now for the next piece, I have to write the domain, which is going to include -1, go up to 3, but not include 3. I know that on this piece, f of -1 is, in fact, -1. So I'm going to fill in this hole with a solid dot. And then I can graph 2x plus 1, but only up to the connection point at 3. And the connection point is not included, so it becomes a hole. When I substitute 3 into the second piece, I get 7. And this is a hole. And again, it is a line. So up to right one, up to right one, up to right one, up to right one. It looks like that. Now, the last piece is the absolute value of x plus 1, but only for values greater than 3. So the domain for the last one is going to be 3 to infinity. But again, 3 is a connection point, so I have to graph it, but as a whole. When I substitute 3 in here, I get 4. That means that this value is going to be at 3, 4, but as a whole, I have a jump in the graph. Now, for all values in this region between 3 and infinity, the absolute value of x is just x. And that will give me, in fact, a line of slope 1. So now I can graph the rest of the graph by using the slope. It is a function. It does pass the vertical line test. It is continuous between negative infinity up to 3, but it's not continuous at 3. And it is continuous from 3 to infinity, but not continuous at 3. This is a function that has a break in the graph, a jump at x equals 3. Let's talk a little bit about the continuity of polynomial and rational functions. They are two of our most favorite functions to model things in the real world. Polynomials are our hands-down favorite of all. For reasons that we're going to discover in this class, you will finally find out why do we harp on polynomials so much. You're going to find out. One of the most important things about polynomials is polynomial functions are continuous everywhere. Polynomial functions, remember, consist of real coefficients. So let's define polynomial. This double bar R stands for real coefficients and whole number powers on x when written in the numerator. Now, what's a whole number? If you don't know what a whole number is, you don't know what a polynomial is. Whole numbers would include 0, so we can get constants, 1, 2, 3, and so on. It's 0 plus the positive integers. That's what a polynomial is. Polynomials, again, can include lines that are slanted, horizontal lines, y equal a constant, parabolas, higher degree, even power functions, cubic functions, fifth power. Those are your polynomials. We love polynomials because they're continuous everywhere and defined everywhere. Their domain is all real numbers, and you can draw them without picking up your pencil over the entire graph. They're our favorite for that reason. And as we're going to learn later on, they're also differentiable everywhere. We can find the derivative everywhere, and they're integrable everywhere. We can find the integral everywhere. That's why they're our favorite. All right, what about rational functions? Rational is second best because it's the ratio of two polynomials. Now, if we have a factor in the denominator, then we know we're going to have a break in the graph. But that value will not be in the domain of the rational function. And it turns out that rational functions are continuous on their domain, which eliminates any 0 from the original denominator. Let's talk about the types of discontinuities that we've been using so far. The 4 discontinuity types are the jump, the whole, the displaced point, and the infinite vertical asymptote. Those 4 you need to know and memorize. I often ask questions on exams, name the 4 discontinuity types, and draw a picture and state which condition of the definition of continuity they fail to meet. So the whole f of a is not defined. The infinite asymptote, f of a, is not defined. And the two-sided limit does not exist because it's not a real number. So it has two problems. The displaced point, the function value doesn't equal the limit value, and the jump, the two-sided limit does not exist. Two of these are what we call removable because redefining one single point would fix the discontinuity. And those would be the hole and the displaced point. To make it continuous, just move the dot to the hole or just fill in the hole. As we're going to learn later this semester, this means that we can actually integrate over these functions because it's a removable discontinuity. Other type, we cannot. The other two are what are known as non-removable. Note that in the removable types, the limit from both sides does exist. When we look at the other two types of discontinuity, the jump and the infinite discontinuity, the two-sided limit does not exist. They don't exist in a jump because the limit from the left and the limit from the right do not agree. They don't exist in an infinite vertical asymptote because they're going to infinity or negative infinity, and that's not a number. Even if both sides go up, that's still not a finite real number. So these are called non-removable, and we'll learn later in the semester that if we have one of these in the graph, we have a problem. For jump discontinuities, remember that the two one-sided limits exist, but the two-sided does not. And remember, for the infinite discontinuity, it's approaching infinity or negative infinity, and that means the limit does not exist. Let's now look at example 3, and let's predict for what values it is and is not continuous. Classify any discontinuity, and then classify it as removable or not if you have one. So let's look at 3x to the 4th minus 4x squared. I don't want you to graph it. I want you to recognize based on the type of function it is. Real coefficients, 3 and negative 4. Exponents on x in the numerator are 2 and 4, which are whole numbers. This is a polynomial. It's defined on the whole number line, and it's continuous everywhere. So this one is continuous on, and you can write double bar R, which stands for all real numbers, or you can use interval notation, and you can write negative infinity to infinity. Notice with infinities, you'll always use round parentheses because they're not numbers, they're directions. If we take a look at the graph of this one, and I did graph all of them for you, you can see right here that it does have a wiggle in the middle, and we'll learn later this semester, it's really fun when we get to chapter 4, how to find the exact values of these relative maximums and minimums. But you can tell you can draw the whole thing without picking it up. If you're worried that there might be a hidden one because Desmos doesn't like to indicate holes, just run your little cursor over it and you'll see it never pops up with an undefined. Now that's not a proof. The proof is because it's polynomial. All right, what about this second one? Pause the video for a moment, figure it out, then turn it back on and let's compare our answers. So let's see how you did. This is neither a rational function nor a polynomial. Remember that the square root of x is x to the 1/2 power. 1/2 is not a whole number, so this is not a polynomial, so it can't be a rational function. It is a function. However, because of the square root, I know the square root's only defined on closed 0 to infinity. but it shows up in the denominator, and thou shalt not divide by 0 in my class. Therefore, we can't have 0 in the domain of this function. There is no other reason why we would have any kind of break in the graph. To have a whole, I have to have a factor that cancels completely from numerator and denominator, and I do not. To have a displaced point, I have to have a piecewise defined function so it can define that piece at some other place. To have a jump in a graph, I have to have a piecewise defined function so I can define it in pieces. To have a vertical asymptote, I need 0 in the denominator that does not cancel. I do have one of those, which means that it's likely approaching 0 like a vertical asymptote. But because it's not defined on the left side, I don't need to worry about the two-sided limit. The two-sided limit does not exist because the function is not real on the left side of 0. Also, the function value at 0 does not exist. So it will fail all 3 conditions of continuity at 0. Therefore, it's continuous on its domain, which is 0 to infinity. Let's now take a look at the graph of this one so you can see what it looks like. You can see in this graph right here that it is approaching 0 from the right as a vertical asymptote like we expected. And otherwise, it's defined and continuous everywhere. Let's now look at example number 5. For what values of x is the function 2 divided by x squared plus 1 continuous? Go ahead and pause the video, work it out, turn it back on, and we'll compare. Okay, let's see how you did on example 5. Example 5 is, in fact, a rational function. 2 is a horizontal line, which counts as a polynomial. X squared plus 1 is a parabola been shifted up 1. It counts as a polynomial. So the ratio of the 2 is a rational function. First 5 letters of rational spell ratio. It is going to be rational, which means that it's continuous on its domain. So look for possible exceptions to a domain. The exceptions would be negatives under even radicals and zeros in the denominator. What else could be a problem? Oh, you can't put a negative or 0 inside of a natural log. And we have some problems with tangent and some other values like that, where allowing a certain angle would cause a 0 in the denominator. So when we're looking at this one, I need to think about x squared plus 1. Nothing cancels, so there's no hole. It can't be a displaced point or a jump because it's not piecewise defined. Do I have a vertical asymptote? Take x squared plus 1, set it equal to 0, and solve. In this case, I get x squared equals negative 1. I know my next step is to take plus or minus the square root of negative 1. But that gives me the imaginary number I. That's not real. It does exist. It's just not real. So the domain here is going to be all reals. When we talk about domain, we're talking about numbers in the real number system. The imaginary number system exists. It's just not real. So it's continuous over its entire domain. Not all rational functions have points of discontinuity. Let's look at this one now. I really like these graphs. I don't know why. It's just very pleasing with the symmetry and the bump in the middle. All right, let's now move on to example number 7 or 6. 6 and then 7. Go ahead and pause the video, work these out, and then turn the video back on and we'll compare and look at the graphs. Let's now look at your work for examples 6 and 7. Example 6 is going to be a rational function because I have a line, which is a polynomial, divided by a parabola, which is also a polynomial. So I know in advance that it will be continuous on its domain, but I have to find out what values might be left out of its domain by determining when the denominator is 0, since the denominator can never equal 0. So I take the original denominator, x squared minus x, say it's not 0, and factor it. This basically means that x cannot be 0 and x cannot be 1. I must have breaks in the graph at 0 and 1. But what type are they? If I put the factored expression back into the original equation for the function, I see that the single factor x cancels and approaches a reduced fraction of 1 over x minus 1. Because the factor x canceled completely, it becomes a hole in the graph. And to find the y value at the hole, I substitute the location of the hole at x equals 0 into the reduced fraction, getting -1. It left the factor x minus 1, which did not cancel in the reduced fraction, which means that instead I must have a vertical asymptote at x equals 1. Vertical asymptotes are not removable. Holes are removable. Let's look now at example number 7. In example 7, we have this function f of x equals x to the -1 plus 1. It's not clear from the beginning what type of function it is. Go ahead and rewrite x to the -1 as 1 divided by x, since that's what a negative exponent does. Then to add 1 to it, I'd like to get a common denominator. It helps to have it written as one term when it's possible. It's not always possible. In this case, I multiply by 1 in the form of x over x, and combining my like fractions, I get 1 plus x over x, which tells me it is the ratio of 2 polynomials. It will be continuous over its domain. Again, the denominator cannot be 0, so x cannot be 0. In this case, because I have 2 terms in the numerator, I am not allowed to cancel. And that means that the x remains in the denominator of the reduced fraction. In other words, it doesn't reduce. That means that I have a vertical asymptote at x equals 0, which is non-removable. Now I want you to go ahead and evaluate the continuity of the function in example 8. Classify any discontinuity you have, and then turn the video back on and we'll compare our answers. Okay, how did you do? This one's a little bit challenging in that it's got an exponential e to the x in it. Again, however, we have the ratio of 2 functions. They're not polynomials, so it's not rational, but it is the ratio of 2 functions. The numerator is the constant function y equals 5, and the denominator is the shifted function e to the x minus 2. Now, e to the x looks like this, and minus 2 just means you went whoop down 2. So what problems with continuity might we have? Well, I need to look to see where the denominator might be 0. I don't have a radical, so that's not an issue. And I don't have natural log, so that's not an issue. No trig function. I'm looking for where the denominator might be 0. That means e to the x minus 2 should not be 0, or e to the x should not be 2. Use your rules that you learned in pre-calculus or college algebra to rewrite this in logarithmic form. The natural log of the answer part is equal to the power. This tells me x cannot be natural log of 2. It doesn't cancel, so it must be a vertical asymptote at x equal natural log of 2. And it is going to be an asymptote in the graph. Let's go ahead and take a look at these 3 different functions. The first one we looked at coming back up here was x and x squared minus x, which is this one. Now, when I'm looking at this one, Desmos again just goes right over the hole like it's not even there. But I know that there's a hole there or something there at 0. When I'm looking at this one, it is a hole at 0. How can I be sure of that? Again, click anywhere on the graph and then drag that point so you're hitting everything in between. Slow down when you get to 0, because at that point it's undefined. That's the only way to know in Desmos that you have a hole. It also has the vertical asymptote at x equal 1. The second graph we looked at was the x to the negative 1 plus 1. And when we looked at the graph of x to the negative 1 plus 1, we found that there was a vertical asymptote at x equals 0, which is not removable. But it is continuous on its domain, which is going to be negative infinity to 0, union 0 to infinity. It's a lot of work to leave a number out of the domain. Here is the domain. And again, you can see that it is not connected at 0 because we have an infinite asymptote. Now let's look at the last example we worked out, which is 5 over e to the x minus 2. Now I went ahead and graphed x equal the natural log of 2 so that you could see that, oh yeah, okay, I see. There is a vertical asymptote at that value. If you scroll out so that you can see it a little bit better as it goes towards infinity, you see that it is in fact the asymptote. The graph never touches or crosses it. I believe we have one more example in this section, which I usually do with my students because I know that this trig one causes a lot of problems and students get a little messed up on this. So let's do this one together. We want to examine the continuity of the function tangent of 2x. Because of the 2 on the inside, we know that it's oscillating faster than normal. Again, we want to classify our discontinuities and then characterize them as removable or not if we have any. So when I'm looking at this, what could cause a problem? With tangent, remember the definition of tangent is that tangent is equal to sine divided by cosine. So the problem isn't the sine, which always bounces between -1 and 1. The problem is with the cosine. And the problem here is that I can't allow 0 in the denominator. So I'm looking at this function, and I know that whenever the 2x turns out to be a pi multiple of pi over 2, again, either pi over 2 or 3 pi over 2, I'm going to have 0 in the denominator. So basically, what I need to write down is 2x cannot be equal to pi over 2 plus any pi multiple. So we can write pi k or k pi, whichever way you want to write it out. The next step, of course, is to get a common denominator here between these two. We need this common denominator so that we can divide by the 2. This is going to give me pi over 2. Oops, my pi and my 2 got connected, plus 2k pi. Take that part off, rewrite it a little better. I multiplied the second term by 2 divided by 2, got the common denominator, and combined them. Now on the left side, I still have 2x. So what I need to do is now divide both sides, since I only have one term on each side, by the number 2. This tells me that x cannot equal pi plus 2k pi divided by 4. All right. Now, to figure out where these values are, what I usually do is I write down what the values of k could be. K could be 0, 1, 2, 3, and so on, or -1, -2, -3, and so on. When k is 0, I get pi over 4. When k is 1, I'm adding another 2 pi to the numerator, so I get 3 pi over 4. A pattern develops where you're adding 2 pi to the numerator each time. So I get 5 pi over 4, 7 pi over 4, moving to the right forever. Moving to the left, it should be similar, but instead of adding, I'd be subtracting 2 pi. So the next one, when k is -1, is negative pi over 4. And the one next to that would be minus 3 pi over 4. Did I subtract right? 1 minus 2 is -1. Yes. And then, of course, negative 5 pi over 4. So basically, I can't have any pi multiple, pi over 2 multiple of pi over 4. That's going to be a problem for me. What kind of discontinuity are these going to be? Well, they're not going to cancel with the numerator. They're not going to come out to be the same. So when we look at this, except for, well, some of them may, let's think about it. Would they come out the same or not? When I take the pi over 4 and I substitute it into the argument, I have a 2 times that, which is going to result in a pi over 2 multiple. Now, the sign of a pi over 2 multiple is either 1 or -1. The cosine of a pi over 2 multiple is 0. So there will be no cancellation, so I'll never get a hole. These are all vertical asymptotes in the graph. Let's now take a look at that particular graph. And you can see that it does have vertical asymptotes very often at the multiples of pi over 4, odd multiples of pi over 4. Now let's talk about continuity over an interval. What does continuity over an interval mean? We've talked about what it means to be continuous at a single point. F of a exists, the two-sided limit as x approaches a exists, and the function value equals the two-sided limit there. But what does it mean to be continuous between 1 and 5? How about between closed 1 and open 5? Or open 1 and closed 5? Or closed 1 and closed 5? What does it mean to be continuous on an interval? We say that a function is continuous from one side, for example, the right, if the limit coming from the right equals the function value there. Now, what does this imply? This implies that f of a exists, that the two-sided limit exists, and the two are equal. In other words, it's the same definition of continuity we've been using before. To be continuous from the right is looking at an interval like either a comma b or a comma b and closed. So in both cases, it's closed at a. If it's closed at a, it means it's continuous from the right. What about continuous from the left? From the left means the interval has to contain the values on the left side of that particular value. So in this case, this would mean that we have some C to A or C to A, and A would again be on the right. And again, this implies that the function at A exists, the limit from the left exists, and they're equal. This is a way of establishing sort of continuity from one direction only. This would be very useful in something like a square root function. When you're thinking about the square root function, remember that it would be continuous coming from the right at 0. The function value at 0 does exist. The function value would be 0. And the limit as I come from the right would be 0. And because they're equal, I could say that the square root of x is continuous on 0 to infinity. If we have an open interval from a to b, not including a and not including b, it's not saying anything about the continuity from the right of a or the left of b. But any value that is not a or b, but is between them, it is continuous there. Now, if we're looking at an interval that's closed at both a and b, then it's continuous from the right at a, from the left at b, and at every point between a and b. If we're looking at one of the form open a to closed b, then it's continuous from the left at b. We don't know what happens at a, but it is continuous at all the points between a and b. And we have a similar definition for closed a to b. Continuous from the right at a, don't know what happens at b, continuous at all the points between a and b. Now let's take a look at the next two examples, example 10 and example 11. Example 10 is relatively straightforward, similar to what I just did with the square root function. In this case, we want to decide what interval the function square root of x plus 3 is continuous over. So in a sense, we need to know where it's defined. That's the first thing. To be continuous, it must be defined. Now we know that thou shalt not put negatives under even radicals and expect to get a real number. You'll get a number, it just won't be real. That means that we're going to pull the x plus 3 out, and we're going to say x plus 3 has to be greater than or equal to 0, which means x is greater than or equal to negative 3. So it's defined on negative 3 to infinity. If we were to graph this one, it's been shifted to the left. That's why it's starting at negative 3. So when we're looking at this one, I think it will be continuous from the right at negative 3 because the function value at negative 3 is going to be 0. And the limit as x approaches negative 3 from the right of the square root of x plus 3 is also 0. The limit from the left does not exist because the function does not exist. Therefore, this one is continuous on negative 3 to infinity. And you can see, if you get it right on the spot, that it is defined and continuous from the right at negative 3. Now let's take a look at this last example. This is a more challenging problem. In this case, we're given a piecewise defined function, and we want to know what makes it continuous. First, I will tell you that exponentials are continuous over their entire domain. So e to the kx is continuous from 0 up to 4. X plus 3 is a slanted line. It's a polynomial, so it's continuous everywhere. For a piecewise defined function, the only point that we have to worry about if all the pieces are continuous functions is the point where they connect. In other words, what happens at 4? I need this part of the graph to connect and touch this part so I can draw it without picking up my pencil. That means that when x is 4, e to the kx must be equal to x plus 3 because my rules are f of a exists. That's rule 1. Rule 2, the limit as x gets close to a from both sides exists and points to the same value. And rule 3, they're equal to each other. Now I've got to establish that the function value exists there and is equal. In this particular case, My brain is kind of going faster than I'm writing, right? So the next thing that we want to write is, what is the value at 4? At 4, we use the second rule because we have 4 less than or equal to x, which means that at 4, I use the second rule, x plus 3. So f of 4 must equal 7. I need this first piece to connect to this ordered pair 4, 7. Now, in the graph of the first piece, I'll have a hole at 4, but that hole has to sit right on top of this point in order for the two pieces to connect. So the next thing I'm going to do is I'm going to write e to the k x has to equal 7. But I know what x has to be. X has to be 4. So this means e to the 4k has to equal 7. Now again, switch to logarithmic form. The base is e, so I'll use natural log of the answer part, 7, equals the power 4k. That tells me that k needs to be the natural log of 7, all divided by 4, not the natural log of 7/4. The 4 is outside the natural log and happens after it. I believe I've found the right spot to make these two connected. Let's go ahead and take a look at the graph and see if in fact this does work. And you can see that I've entered the equation to the graph right here. You can see that I've got this natural log of 7 divided by 4 times x, but I'm only graphing between 0 and open 4. Then I want to turn on the graph for the second piece, x plus 3, between 4 and 8. Why is it not coming on? Why is it not coming on? Good question. Okay, I'm not sure about that. It should be coming on. Oh, it's off the graph. That's why. Duh. Okay, there we go. So you can see that the exponential part starts here and goes up, and then the linear part connects. And notice that right here, they're at the same spot. On the exponential function, it's a hole, but on the line part, it's filled in. So they actually connect. You can draw without picking up your pencil. Okay. Let's now move on. I'll recenter my graph for the next one. Let's now move on to the next part, which is continuity of a composed function. What does it mean to compose a function? To have a composed function means you placed one function inside of another function in place of the variable x. So for example, we could have a function such as sine of x squared plus 3. The inside function is x squared plus 3, and we could call this one g of x. The outside function is actually sine of x. Let's rename this one h, and we'll write f of x equals sine of x. So when I compose f with g, I get h. The question is, if I know something about the continuity of the outside function, like sine, and I know something about the inside function, x squared plus 3, can I say something about the continuity of the composed function, sine of x squared plus 3? And the answer is yes. Let's now take a look at the next piece, the composite function theorem. The composite function theorem is a little bit tricky, a little bit confusing. It says, assume the function f is continuous at a point at L, and the limit of the inside function g of x as x approaches a is that number L. Okay, let's throw some numbers up here so this makes more sense. Suppose f of x is continuous, and I'll abbreviate, at x equals 8, and the limit as x approaches 2 of g of x equals 8. Then the limit of the composed function as x approaches 2 of f of g of x is going to be f of 8. All right, let's pull it apart and talk about it again. It is a confusing function. Basically, f of x, the outside function, has to be continuous at the x value, which is the y value that came out of g after I substituted 2 in. So the original value that the limit is approaching for the composed function first goes into g, produces a limit value, say 8, and then takes that 8 and puts it into the outside function. As long as I know that g of x is going to give me a limit value here, and I know f is continuous at that value, then I know that the limit of the composed function will be the outside function at the value of the inside limit. Now, how do you apply this in practical terms? In practical terms, if we're looking at example 12, we do what we've always been doing. This is a composed function. The inside function, g of x, is equal to x minus pi. It's a line, crosses the y-axis at 0, negative pi. The outside function is the sine function, sine of x. So the question is, if I take the value of pi and I evaluate the limit of the line as it approaches pi, well, I know the line is continuous everywhere, so I can just substitute it in. And then I'll get out the value of 0. Well, that 0 is going into the outside function. Is sine continuous? That's required. Yes, it is. You can draw the sine graph forever and ever without picking up your pencil. So it is continuous. So when I substitute the 0 in, I get sine of 0 is 0. In other words, we do what we've been doing. We just keep substituting the value in. This works because sine is continuous and the inside limit does exist. And this will give me sine of 0, which equals 0 for my solution. I want to say one more thing about composition and continuity. This turns out to be a hugely important theorem. What it tells us is that composing continuous functions together is still going to be continuous on the domain where it's defined. So if I were to write something really crazy, like f of x equals e to the x squared plus 2 natural log of x minus sine of x, and I've got this crazy power inside an exponential, I have no idea what it looks like, but I can guarantee you that it is continuous on its domain. And the domain has to satisfy all the component parts. X squared is defined everywhere. Natural log is only defined on 0 to infinity. Sine of x is defined everywhere. E to a power is defined everywhere. So natural log is going to restrict our domain to be from open 0 to infinity. Let's look at this graph and see if it is in fact continuous on 0 to infinity? And you can see that, in fact, it is. And it's actually giving me a value at 0, which is a problem. Interesting. We found a glitch in the software for Desmos. That should be undefined, right? Because the natural log of 0 is undefined. So it should be undefined. But we can see that it is continuous as it goes off to the right. I didn't know about that glitch. Okay, let's now talk a little bit about continuity of trigonometric functions. Trig functions are basically continuous over their domain. Now we know that the graphs of tangent, secant, cosecant, cotangent all have vertical asymptotes. But those vertical asymptotes cause 0 in the denominator, so they're not in the domain. So we're talking about where it's defined. As long as it's defined, it's continuous. That means that sine and cosine are continuous over the entire real number line. Let's now turn our attention to our last topic for today, which is the intermediate value theorem. This is another very important concept because the intermediate value theorem leads to what's called the mean value theorem. The mean value theorem is used to prove the fundamental theorem of calculus. So it's pretty important. When we're looking at the intermediate value theorem, the idea is pretty straightforward. It says if you have a closed and bounded interval, meaning you can't go to infinity or negative infinity, you have to be going between two finite real numbers, like 1 to 10. If you take any real number that's between f of a and f of b, so let's pretend that a is 1 and b is 10, then f of a is f of 1, and let's just suppose that that's 2, and f of b is going to be f of 10, and let's suppose that that's 20. Right? So it says, if I have a continuous function on closed 1 to closed 10, then I take any other number between f of 1, which is 2, and f of 10, which is 20. There has to be at least one point C between a and b, 1 and 10, whose y value is that number. Has to be. In other words, you can't get from one point down here to another point up here continuously without hitting every y value in between. That's the intermediate value theorem in a nutshell. When you think about driving on the freeway, you cannot drive 60 miles per hour without having driven 55 and 35 and pi miles per hour. Speed is continuous. You have to pass through every single value to get to another one. Now, what places do we use this theorem? We often use the intermediate value theorem to prove that an x-intercept or 0 exists for a function. How can we do this? Well, again, if we're looking at a graph and we want to know for sure where it's got some zeros, and by zeros I mean these x-intercepts that we have here, then all I need to do is find an interval over which one of the y values is positive and the other y value is negative. If it's a continuous function, it can't get from the negative to the positive or reverse without going through 0, which means that when I'm looking at this, as long as one y value on the interval is positive and one y value on the interval is negative, I know a continuous function must have an x-intercept, at least one, between them. Now let's take a look at applying this theorem. I want you to work out the problems 13 and 14. looking for whether or not we can prove that there is an x-intercept or 0 over these intervals. Pause the video, work it out, then turn it back on. Let's take a look at example 3. To use the intermediate value theorem, it must be a continuous function. But this is polynomial, which is defined everywhere and continuous everywhere. To find out whether there is a 0 or x-intercept between x equals 0 and x equals 1, I substitute 0 and 1 into the function. F of 0 is 1, which is positive, and f of 1 is -2, which is negative. A continuous function then has to go between every value between 1 and -2, which means it has to pass through 0, because 0 is between -2 and 1. There must be a 0 in between A and B. In our case, the A and the B are 0 and 1. And note that it's in open 0, 1, not closed. Let's take a look at the graph to verify our conclusion. When we look at the graph, I've put in all the points so that we can see them. You can see the value at 0, 1 and the value at 1, -2. It's a continuous function, so you have to be able to draw from the purple dot to the black dot without picking up your finger, which means you have to cross the x-axis at least one time. And we did indeed do that. Let's now turn our attention to the next example, which is our last example for this section. This is a rather more difficult problem because of the function and because it's not defined as a function to start. In the beginning, it just wants to know, is there a solution for x to the equation 2 to the x equals x cubed? Well, to test this, I can still use the intermediate value theorem. Even though there are two functions and I'm wanting to know if they're equal to each other, which may not be on the x-axis, I can instead take this, set it equal to 0, and then create a function. I created 2 to the x minus x cubed. You might use x cubed minus 2 to the x. Both will work and give the same result. When I look at this, I then substitute the endpoints of my closed intervals into my defined function and work out the values. The first interval is between 1.25 and 1.375. The function value at 1.25 is positive, very small, but positive. The function value at 1.375 is tiny, but it's negative. 0 is between these numbers, so there must be at least one 0 between them. Looking at the function value at 1.5, it's a -0.55. Well, I'm guaranteed that between 1.25 and 1.5, there is a solution. But I am not guaranteed that there is an x-intercept over the interval 1.375 to 1.5. Let's now go ahead and take a look over here at these particular graphs, and then I'll show you something pretty amazing. It's very hard on a Desmos graph to tell whether or not this particular point is on the axis. You'd have to zoom way in to see that it's actually below. If you want to do that, you can scroll your mouse wheel and just go in, and then we'll have to move it sideways. And then you can see that, in fact, it's not touching the x-axis. It is below. And in our particular case, we notice that there is not, in fact, a solution between 1.375 and 1.5. The intermediate value theorem can't tell us it's not there. It can only tell us if one is there. Let's now take a look at the original question, which was, is there a solution to 2 to the x equal to x cubed? I'm going to type in the function 2 to the x and graph it, and the function x cubed and graph that function. Now, when I do that, the question is there a solution? In fact, it looks to me like there's more than one. Let me take off this function, but leave on my points. All right, maybe make this one a different color. Let's make it red. Okay. And let's make the cubic black, since green doesn't show up too well for people with color blindness. So when I'm looking at this right now, I want to know, does the blue curve touch or cross equal the black curve? It does, right up here. And if I look at this one right up here, if I can get it right on, it says 1.373, 2.591, blah, 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 blah. Now let's see if I can get this one to come on. Do you notice anything about this point that we found that was the x-intercept for intermediate value theorem? That value there, 1.373, is the x-coordinate of the solution to the original problem, which gives you another way of solving problems. This is the end of the video on continuity. The next video will be discussing, finally, the formal definition of the limit. It's rather difficult, so make sure you bring your game face. I'll see you there.